Good morning, good afternoon, good evening, everyone. Thank you for joining our Stantec Water webinar series today. We're going to talk about the state of art when it comes to selenium management and regulation. A little bit of housekeeping before we get started. First, you're going to be muted during the presentation, but you can ask questions at any time using the GoToWebinar questions option. We will get to those with roughly 15 minutes left in the presentation. And we'll try to get to as many of your questions as we can. If we don't happen to get to your question, we'll follow up with you directly offline. You'll also receive a professional development hour credit, or certificate, I should say, that you can submit to try to get credit to your local certifying agency. I usually send those out within a week or so after the event. And with that, I'm going to turn it over to our presenters who will kick off the presentation.
Great, thank you, Ryan. I'm Brenda Bailey. I've been working in geoscience for over 15 years. I've been involved in the technical assessment and evaluation of selenium-related projects as both a regulator in British Columbia and a consultant in the mining and power sectors. Today, I am joined with my colleague, Rob Simm.
Hi, my name is Rob Simm, and I've been involved in industrial water and wastewater treatment now for over 30 years. And I've been involved in over 10 selenium treatment projects and counting. And I have a number of publications on selenium that we've drawn a lot of our information from for this presentation. So today, Brenda and I are going to talk about why selenium is an issue, the basis of the current regulations, state-of-the-art selenium management, and then we're going to talk about the selenium treatment methods, whether they be physical, biological, hybrid, and then some of the issues in the current technologies. We're going to talk about recent developments in selenium management and treatment, and then we're going to wrap it up with what is the best management approach for your site, and then open it up for questions.
So why is selenium important? Selenium is a naturally occurring constituent in the environment, and it varies in concentration across geographic region. It is a unique element in that it exists in many stable isotopes and in different oxidation states. It is a non-metal on the periodic table, but it acts like a metal, even replacing sulfur in some amino acids. Selenium is an essential trace element needed for maintaining proper health of humans, animals, plants, and microorganisms. It's found in general supplements and multivitamins that we take every day to help with our metabolism and thyroid. However, at too low or too high of concentrations, selenium can have detrimental effects.
Brenda, I'm going to jump in here. Your slide's cutting off. Do you mind maybe taking it out of full screen and then resharing again? Let's see if we can fix that.
Sure.
Not sure what's going on.
Can you see it?
We see the notes view. Yep. Let's try the slideshow now and see if it'll.
You see it now?
No, it's still doing the same thing. It might be your monitor resolution, so we may have to let me present. And you'll just have to tell me when to switch the slides.
Oh, sorry about
that. Are you seeing the full slide view, Tony? Or just half the slide? Or is it cut off? Someone has commented it's still cut off. Okay. Sorry about this, everyone. A little technical glitch. Let me see if I can make it work on my end. All right. Give me one moment, please. All right, how are we looking now?
Looks good to me.
Better, okay. Let's get back to your slide. All right. go ahead and just say next,
Okay.
Brenda, and I'll advance from
Sure.
there. All
Sounds
right,
good.
back to it.
Okay, so selenium cycles through the environment in different speciation states from, or for example, inorganic species, which are often found in aqueous environments like surface waters, groundwater, wetlands, and organic selenium compounds, which are more readily found in air, soil, and plants. Selenium speciation and geochemical reactions control the mobility of selenium under specific environmental conditions, like either reducing or oxidizing conditions, which ultimately control the fate of selenium, either attenuating or mobilizing selenium. Natural processes account for 50 to 65% of selenium emissions by natural weathering and soil leaching processes of sulfides, whereas anthropogenic activities like metal refining and processing, coal combustion, mining activity, and fertilizer application to agricultural lands can account for about 40% of selenium emissions. Slide. So why is selenium an issue? Well, its most negative property is its ability to bioaccumulate in the aquatic food chain, starting with the lowest trophic levels like algae and plankton up to animals like predatory birds and waterfowl. And this happens despite being at low concentration levels above baseline conditions. We're talking in the low parts per billion as compared to other toxins. Selenium uptake is dependent on the state of selenium in the environment. For example, inorganic selenium bioaccumulates up to 100 to 400 times, whereas organoseleniums can bioaccumulate upwards of 350,000 times. The documented effects of selenium on these higher trophic species include mutations and developmental abnormalities in fish larvae and embryo mortality in birds, both of which can impact population levels. And this transition from no effect to reproductive failure in fish can occur within a range of a few micrograms per liter. Slide. So the basis of the current water quality regulations is complicated by all the factors that I just described. Next slide. And the most sensitive species near your site will be those predatory fish and water birds, which feed on other fish and water organisms. A number of studies have been done on the tissue of the most sensitive receptors, and the information has then been used to develop food web models, starting with the higher order consumers and back calculating down the food web to estimate water column concentrations with little consideration of the environment in which the species lived. Yet the relationship between water and other compartments within the environment, like sediment and algae, are site-specific and complex. So these back-calculated water column concentrations from these food webs models are being used as guidelines. And this is a simplification of a complex problem, and it leaves one to wonder, are the guidelines too restrictive, and what does it mean for your site? Next slide. On a global scale, most guidelines are based on human consumption, whereas in Canada and the US, they generally consider the health of the aquatic environment with progressively more stringent guidelines over time. And this has resulted in an increase in public awareness and a need for selenium management and treatment. Because bioaccumulation and toxicity of selenium to organisms, it cannot always be predicted consistently from concentrations of selenium in water. Some scientists have advised against the use of a water column guideline at all. And this is still up for debate, but water is the more easily measured media and does not require sacrificial sampling of rare or endangered organisms. So the guidelines are based on the most easily measured metric, but the natural system is likely site-specific and species-specific. So the bioaccumulation models used to develop the guidelines doesn't really account for this, with the exception of a consideration for the propensity of selenium to accumulate in lentic and lotic environments, or more commonly understood as slow-moving water versus fast-moving water. But it's not just because of the speed of the water, it's more about the natural environment created by the differing conditions. And because of the complexity surrounding selenium uptake and the current state of science, it's unclear if the guidelines are too conservative or overly restrictive. The range of selenium guidelines in the aquatic environment tends to be 10 times lower than that in drinking water. So that's 1 to 5 microgram per liter in aquatic environments and 10 to 50 microgram per liter for drinking water. Slide. So in BC, guidelines for selenium in the environment are set by federal and provincial governments, but discharge criteria are currently set in permit authorizations at that provincial level, with federal regulations pending. Permits set the site-specific discharge criteria and compliance monitoring location limits. And these criteria, again, depend on those most sensitive receptors and have ranged from 5 ppb up to upwards of 20 ppb. So water treatment requirements to meet these low concentrations in the receiving environment are becoming more onerous, and in some cases are ahead of the science, in that water treatment to meet these low guidelines is very hard to do. And this leaves us in a state where the permitted operational requirements are very difficult to achieve. Slide. So where are we at then with selenium management? Slide. Well, the best place to start is to not have the problem to begin with. Selenium management methods include the same ones considered in the MLARD policy in British Columbia, that being avoidance of reactive materials is the #1 mitigation measure. But when that can't be achieved for, say, neutral leaching constituents like selenium, other tools should be deployed, and that's things like subaqueous disposal in backfill pits, in underground workings, or in artificial impoundments to limit the availability of oxygen, thereby preventing or limiting the mobilization of selenium from sulfide minerals from the beginning. Cover systems or water diversions can also be used to limit water and oxygen content. And in British Columbia, water treatment is to be considered the mitigation of last resort, but ultimately, when waste management measures aren't employed or aren't sufficient to meet the requirements, treatment may be required. Passive and semi-passive treatment systems are proposed in some jurisdictions to be used as a mitigation for selenium, including suboxic saturated zones in backfilled pits and wetlands or constructed systems. And these might be good options where selenium issues already exist, but face tough regulatory scrutiny to get buy-in for new projects. And then when all else fails, active water treatment might be the only available option. Next slide. So improved waste management practices still require research. Many conceptual plans have been discussed over the years, but few have been deployed at a large scale. And operator control and site constructability in real time may prove challenging. Add the complexities of long-term physical and chemical stability of structures in light of things like the global tailing standards, and we have a lot of research and field trials still to do. It makes it challenging for decision makers to rely on conceptual plans that still require demonstration, and operations should have well-established contingency plans when posing a novel approach to waste management or water treatment. You need to bring the regulator along for the ride in order to get buy-in before they are faced with impractical decisions. Next slide.
So when all else fails and you've tried to manage the situation on site and you're faced with treatment, what are your options? Slide. So you know, when you look at where we're at with selenium treatment right now, it's been practiced in the mining, power, oil and gas, and ag drainage sectors for a number of years. But when you actually look at the number of treatment plants that have been built between now 2006 and now, it's maybe 40 installed in North America with capacities of anywhere between 25 and 5,500 plus GPM. So it's not a tremendous number of systems, and I think it's fair to say that our experience with these systems is still we're still gathering experience with selenium treatment. Slide. So one of the things you got to remember if you're looking at mining specifically is that in addition to selenium, you're going to have other contaminants that you're going to be concerned with, and they have an impact upon the treatment efficiency and efficacy. Slide. So if you've got a mine impacted water, in many cases you're concerned about nitrates, and you've got concentrations anywhere from 20 to 100 plus milligram per liter. You've also got selenium in the oxyanion form, selenate, selenites, and then you've got sulfates that you've got to be concerned with, and with concentrations in the 600 to 2,000 plus milligram per liter range. And depending upon the treatment method that you're looking at, those four contaminants can compete. Next slide. So in terms of treatment methods, I think it's fair to say historically, people started looking at physical chemical treatment options. Ferric precipitation at one point used to be the EPA best available technology for selenium removal. Low cost, relatively simple. The issue is that it's great for selenite, but not very effective for selenate. And unfortunately, selenate is the prevalent form of selenium in mine impacted waters. Reverse osmosis, you can achieve very low levels of selenium in the effluent, or in other words, high selenium removal. But the disadvantage is it produces a brine that has to be managed, and that's relatively costly. But there's a number of vendors that can provide this. Recently, probably in the last 4 to 5 years, ion exchange has started to gain a little bit more interest. BQE has a process for a selenate selective media. The disadvantage is that you have to have, if you've got nitrate in the water as well, then you've got to have a separate nitrate removal step. And then zero valent iron has been looked at by a number of folks. It can remove selenite and selenate depending on the configuration. There's a lot of research now going on in China with nanoscale ZVI, but passivation and the ability to get down to ultra low levels is still a concern. Next slide. So very briefly, ferric chloride precipitation. What happens is that the ferric chloride produces a ferry hydroxide complex, and the selenate actually, or selenite, I should say, absorbs to that. And the overall efficiency, again, depends on your selenium speciation. Slide. RO, again, you can get very high removals, 95 to 99 plus percent, but the concentrate is problematic to deal with, and it can be costly. Slide. And we've already talked about ZVI. One of the issues with ZVI is that To my knowledge, there's only really one operational plant in North America, and the actual retention times required for selenium treatment are relatively long. Slide. I'm going to spend a little bit of time on the ion exchange. You can get down to very low levels of selenium. It appears to be cost competitive with biological. There's the residual itself. So with ion exchange, you get a regenerant. You need to basically regenerate the media, and the process that BQE uses an electroreduction circuit to regenerate treat the regenerant, so to speak, and that produces an iron selenium solid cake, which appears to be possible to take off-site and put into as a feedstock for steel production, which has some advantages. But again, you've got a need for a separate process for nitrate removal. Next slide. So I guess the question people will ask is, where has this been done before? And there was one full-scale operational plant at Kemess, at the mine site there. My understanding is that Kemess is in care and maintenance, so the facility has been shut down. But this is an application of the ion exchange process. Next slide. So let's talk a little bit about biological treatment. Slide. Virtually all of the biological treatment applications are based upon taking selenate and selenite and reducing them to elemental selenium with bacteria. That is the science behind all of these. The thing you got to remember when you do biological treatment, though, is you've got selenium at a parts per billion level, typically in a mine impacted water. You also got nitrate in the water, and many of those same bacteria also reduce nitrate and nitrite to dinitrogen gas. And the nitrate is typically 2 to 3 orders of magnitude higher in concentration, or sometimes 1,000 times higher than selenate and selenite. Next slide. So the fundamentals of biological treatment: the bacteria grow and sustain themselves through oxidation reduction reactions. So what does that mean? It means that you need an electron donor. You need some sort of a substrate that you've got to add. It's typically not available in the mine impacted water, and you're going to need a carbon source. When you add those materials, those electron donor materials, you're going to grow bacteria, and you're going to have a residual, biomass residual that goes with your process. Next slide. So the electron donor is typically a substrate. That could be acetate, methanol, micro C. The carbon source is typically one and the same as the electron donor. But in many cases, you also need a macro micronutrients. And phosphorus is typically added in these processes to basically get to sustain the biological treatment because it's not available in high enough concentrations in the mine impacted water. So these kinds of things are important because they have an impact on the efficiency of the process, the amount of equipment you need, and the cost, both capital and operating and maintenance costs. Slide. So in terms of biological, what are your options? There's a whole host of active biological treatment options. They include everything from upflow anaerobic sludge blanket reactors to some of the attached biofilm reactors like packed beds, fluidized bed reactors, moving bed biofilm reactors. There's semi-passive, which there's a lot of interest in now. They include saturated rock fill and gravel bed reactor. Slide. And there is still a significant interest in passive systems. And the rationale for that is the lower capital and operating costs. However, our experience has been that because of the low levels of selenium that you typically need to meet the regulations post-treatment, that the passive systems don't provide as reliable a performance. and it comes down to what drives those reactions. The biological reactions are driven by the addition of the electron donor, and to get down to low levels, you need to have control of that electron donor and the macronutrient control, macronutrient addition. Next slide. So, like I said, let's look at some of your options here. Passive wetlands biochemical reactors, people have tried these. I'm going to just very quickly go through some of the details on some of the more on the biological treatment options. If you want more information on those, IWA just is going to be publishing a book on environmental technologies to treat selenium pollution. It comes out in August, and chapter 6 of that book is all about biological treatment and has more detail than what's going to be presented in the webinar. Next slide. So, biological treatment, 3 main vendors in North America. One of the first questions people ask is, well, who shall I call if I want a system? Suez, which is now soon to be Veolia, Frontier, which is owned by Evoqua, and Envirogen are the 3 main vendors. Veolia has an MBBR reactor that they use, and they had 3 sites previously. All of these vendors use fixed film processes. Suez is the downflow packed bed reactor, or the AB-MET process is what you might know it by. Envirogen uses a fluidized bed reactor, and Evoqua or Frontier, 2-stage process that is basically a combination of an FBR without recycle and the downflow reactor, packed bed, and it comes under the trade name Seahawk. Next slide. So a lot of what we see in the marketplace for selenium treatment is really historical. If you look back, the first selenium treatment processes, they came into being in the mid-90s, early 2000s, and it was a company by the name of Applied Biosciences that really formed and developed the AB-MET process. They did a number of mining projects. They were purchased by GE and became part of GE Water. Then they were, GE Water did a number of selenium treatment plants for Duke and in the power industry. I think the next watershed moment was really in 2012 when Frontier launched, and they developed the Seahawk process, and their first, I think their most important project at that point came in 2015 for the J.R. Simplot company at the Smoky Canyon mine. And then about 2013, Envirogen did the work with the fluidized bed reactor at Patriot Coal, and then the West Line Creek plant in 2014 for Teck in British Columbia got underway. About that same time, there were 3 mine sites in West Virginia that went to moving bed biofilm reactor, which was the Veolia process. That gives you kind of a quick overview of kind of the history of how we got to the basically the 3 or 4 main vendors in the market. Next slide. So in the there's been a lot of activity though in the last 3 years, and as Brenda alluded to, you know, there's a lot going on in selenium. There's a lot of the science is still evolving. In the last 3 years, advanced oxidation has been used to address organoselenium species. We found that organoselenium species, because they bioaccumulate at a much higher rate, in some cases need to be dealt with. BQE's SelenX process applied at full scale at CAMES, I think is a big step in the last 3 years, because that's a non-biological process. Teck has completed demonstration trials of saturated rock fill at scale, which is a semi-passive biological treatment, which is a really big step in the evolution of selenium treatment. And then ASU has published the CSANS process model for biological system optimization. And the reason that this is important is a lot of these systems were originally designed empirically And now we've got a fundamentals-based model that will allow us to optimize these systems, the sizing and the operation. And then finally in 2018, EPRI brought a number of people together at a global summit, and people with all having issues with selenium, and brought these people together to talk about how we could form a Selenium Center of Excellence to really share information and experiences and identify research needs in the selenium area. Next.
Okay, so for the semi-passive system example, we have a saturated rock fill. So the concept of an SRF is to create an anoxic condition in the fill material to promote the reduction of selenate and selenite to elemental selenium, and thereby attenuating selenium. So for coal mines, waste rock seepage tends to have some dissolved organic carbon, but when there isn't a suitable carbon source or adequate amount, supplemental carbon is needed to attenuate the selenium and nitrate. And similar to active water treatment systems, a managed SRF requires this addition of a carbon source and nutrients to facilitate that attenuation. Slide. So this is a diagram of a conceptual SRF. Here in the center, you have the SRF, and you can see on the far left-hand side, you start with your influent in a breaker tank, which feeds water into the SRF through injection wells, which are also loaded with your tracers or reagents for the process. You also have monitoring wells within the system. And on the far right side, you have your extraction wells for water withdrawal and buffer ponds to store treated effluent prior to discharge. This appears to be simple, but also consists of many tanks, pipes, pumps, etc., similar to what you'd see for an active water treatment plant. But the advantage of the SRF system is that it's projected to be about half the cost of a system that is similarly sized active water treatment system. Slide.
So combination technologies, and one of the things that we're seeing folks look at is how can we now combine some of these technologies together. Iron precipitation or ferric chloride precipitation biological is used routinely in power. And if you've got a high selenite concentration or a higher selenite concentration, that can be used in combination with biological. RO with biological is an interesting combination. It's what's used at the Smoky Canyon Mine by Simm. And then recently, I know BQE is looking at RO with their electrochemical reduction cell as another option for combination treatment. Next. So this is an interesting project because I think it's a good illustration of the state of the art. This is I know that the Simplot company put a lot of thought into this. In this particular project, the mine impacted water comes in. They use ultrafiltration, reverse osmosis, which you can get down to a very low selenium concentration, less than 0.5 parts per billion, and then they do RO biological treatment of the RO concentrate, and then they blend the effluent from that back into the actual effluent from the RO, and I know that this has worked out quite well for them. Next slide. So what are the issues with the current technologies? Next. Well, they're complex, and this is a BIM model from a treatment system, and you can see it's lots of pipes, lots of pumps, lots of units, so they're complex. Next. It's not cheap. You know, I think it's fair to say that the capital and and O&M cost for these systems is quite high. And the numbers that I'm presenting here, a lot of these have been published and gives you an indication of kind of numbers that you're looking at. Next. One of the things that we're finding is there's a number of different selenium species with differing toxicities. And when you produce organoselenium species, you can have issues with even though you have a very high treatment removal efficiency, that you still have not reduced the toxicity to a low enough level. Next. And there's lots of room for improvement on existing designs. You know, both the power and mining industries have spent a lot of money, tens of millions of dollars, on pilot testing for biological selenium removal in particular. We know that there's competition between nitrate, selenium oxyanion, and sulfate reducers. And there's really a lot of need for predictive models. And that's why this ASU CSANS model is so important. And to try to reduce the costs and the need for pilot testing and help us optimize designs. So a lot of room for improvement on existing biological designs. Next. And one of the things that is still an issue for the industry is, what's the long-term fate of sequestered selenium? So if you've got an active treatment system, you're going to have a residual. The bacteria will convert the selenate and selenite into elemental selenium as a nanoparticle. It's typically attached to the biomass, and then you got to do something with that residual. You put that residual into a landfill, and then that has the capability to come out of or be remobilized in the leachate. So, you know, trying to find methods to basically sequester the selenium long-term are important. And then if you go to a semi-passive system, you've sequestered the selenium in situ. And what happens when you stop adding carbon and nutrients? And how long is that selenium going to stay there? And I'm not saying it's not going to stay there in perpetuity, but I don't think we've been operating some of these systems long enough to know what the long-term fate of the sequestered selenium really is. And then selenium has an economic value, not only to the high tech, but to the ag sectors. And is there an opportunity to recover the selenium and put it to use, good use, and take it off site? So those are the things that really need a little bit more study. Next. So, and then when you look at the state of the science, a lot of people will ask, well, okay, what about new technologies or new processes? Well, they take time and money to get regulatory approval, and they take time to get on track and to basically be implemented. And it can take years and sometimes decades before you get a new treatment process at the operational stage. Next. So, recent advances. Next. Probably some of the most important we've already talked about, but the CSANS model is really an important development. The development began in July 2018. It was a partnership with EPRI, ASU, and Stantec, and it's really a mechanistic model that is allowing us to actually look at a lot of these biological treatment processes and optimize them, optimize the sizing, and optimize the operation, and therefore help us optimize the cost. And that's one of the more important, I think, developments in the last 4 to 5 years in the treatment side of things. Next. And this is basically just a screenshot. It's the model itself is a model that was it's an add-on to the Sumo platform that was developed by Dinamita, and I know the folks at ASU have put together a very extensive model that I think is going to help the industry immensely. Next slide. So, are the regulations ahead of the science. You know, as Brenda said, the regulations are based on current food web models for the most sensitive species. And in some cases, and people would argue that, you know, they are too conservative. So you have conservative water, and being conservative is appropriate in a regulatory situation. But that results in conservative water column targets and low discharge limits for the effluent from mine impacted water treatment plants. And meeting those ultra low limits costs a lot of money. And then you've got treatment designs that were initially empirical, and there's a lot of room for optimization. And when something's not optimized, it tends to cost more. Next slide. So passive doesn't appear feasible in many cases because of the low limits and the need to meet the regulatory requirements on a regular basis. Semi-passive appears more cost-effective than active treatment, and in some cases, when you look at the economics, semi-passive can be roughly half the cost of active treatment, but the risk associated with the long-term fate of selenium is still a question. So, you know, when you look at what needs to happen here, more emphasis needs to be placed on waste material management to avoid selenium mobilization in the first place. And then there needs to be a lot more work on selenium speciation, and the conditions under which organoselenium species are produced needs further study. Next slide.
So to close, we'll leave you with some food for thought. Like Rob just said, the best option for selenium management is to minimize waste drop contact with oxygen and water by managing your wastes. Reuse your mine impacted water as much as possible and divert clean water away from your waste materials. And no treatment option appears to be perfect. The situation is fluid and uncertain, and you need to stay flexible with layers of contingency plans. So thank you, and we'll take questions.
Great, Brenda, Rob, thank you very much. We have lots and lots of questions. So thank you to everybody that's submitted those. And Brenda, I'll go ahead and let you lead the Q&A here. So if you want to just go through and grab the ones and go from there.
Okay. So I'll start with one of the first ones here that should be pretty easy for you, Rob. Do you expect pH to drop during the biological treatment?
It depends on the process, but not extensively, no.
Okay, just going up to another one here. 1 second. So you mentioned there's a secondary market for selenium. Can you describe a bit more about how that would work?
So the selenium, there's a lot of research that's being done on selenium recovery, most of it out of Europe. You know, selenium doesn't have a really high economic value at the current time. It's about $20 per pound. However, when you look at the source of selenium, the source of selenium is typically slimes from copper processing, and the amount of selenium associated, the actual amount of selenium that you can get from copper processing, that the actual reserves are estimated to be less than 50 years. At the same time that selenium is, the number of uses for selenium is expanding as a feed additive for animals, farm animals, as a additive for solar cells, and it is also used in the medical field for a number of pharmaceuticals, anti-cancer drugs, anti-diabetic drugs, all sorts of things. And so I, for one, and I think I'm not alone in this, think that there's going to be an increase in the actual market for selenium, and with any luck that the actual market for the actual marketability of the selenium that you're removing the actual science will catch up with the market, if that makes any sense.
Yeah, I think so. So we'll move on to another question. This one's about the Comess plant. Is the Comess plant treating mine impacted runoff water or treating process water treatment plant effluent? So it's a bit mixed because I think they made a typo here. So I'll just read it verbatim and then we'll fix it. Is the Comess plant treating mine impacted runoff water? If it is in care and maintenance and treating runoff, then maybe the plant is still operating. Do you know if it's been mothballed or is it actually running site water through the system?
Yeah, when I talked to the folks at BQE, my understanding is the plant has been shut down. It's not currently operating, and I don't know why, but that's what I've been told. It operated for approximately 1 year with good results.
Okay. People are adding questions and it moves my screen, so just bear with me a second. Does SRF/passive treatment require AOP for organoselenium?
That's a really good question, and my understanding from the folks we're involved in a project right now, a confidential project, not in British Columbia, and the testing we've done doesn't appear that we're going to need AOP.
Okay. Does water with high TSS need pre-treatment for all biological treatment options?
So the short answer is yes. Well, let me back up. The short answer is maybe, I guess is probably a better way to put it. And to be more specific, if you look at something like a packed bed, the AB-MET process, packed bed will typically, require pre-treatment when the total suspended solids is north of 50 milligram per liter. And if you look at a fluidized bed reactor like the EnviroGen process, it has a much higher capability to take TSS than a packed bed. And you would start looking at pre-treatment when the TSS gets close or over 100 milligram per liter.
We have lots and lots of questions coming in, so just a reminder, we'll try to follow up with you directly if we don't get to your question, and we just put Rob and Brenda's contact information in the chat, so you can also follow up with them directly if you'd like as well.
So hopefully that answered the question, Brenda.
Looks like Brenda dropped Rob, so I'll jump in here and ask some questions.
Okay.
Sorry about that, everybody. The joys of working from home and technology. All right, let me see if I can find you a tough one here, huh? All right. Given the uncertainties of various solutions in your comment about layers, does this suggest investment is prudent in multiple technologies, supplying something like the factor of safety of greater than 1?
So I think the point we're trying to make with the presentation is it's important to understand that the requirements are stringent, okay, from a treatment perspective. The science is still evolving in many respects, and it's important to be flexible. And you can see this in some of the permits that are written, and where somebody will go with a treatment option, even if that treatment option might not be, the science hasn't caught up.
Okay,
The regulator, are you still there, Brenda?
I am now.
Okay, the regulator will ask that you have a plan B if your treatment process doesn't perform as anticipated. And so I think it's important to when you design your treatment process or whatever your management method is, design it in such a way that if you had to add an additional treatment process or you had to bring in a temporary treatment for some reason, that you could do that. That's really the message that we're trying to give.
So I missed which question you answered, so I hope to not ask it again. But I'll just ask another one here. Are phosphorus additions required for biological additions requiring any post-treatment to deal with residual phosphorus in the environment?
So typically, as indicated in the webinar, you have to add phosphorus for the biological treatment because there's not in most cases there's not enough phosphorus in the mine impacted water to drive the biological reactions, and you do have to have a some sort of a method or way to reduce phosphorus prior to discharge into the environment in case you add too much. We've got a project that we worked on where the operator actually is able to judiciously add enough phosphorus that they don't need to treat for phosphorus on the back end. But you should have something there just in case. So short answer to your question is yes, you need some sort of phosphorus removal at the back end.
Did you answer a question about wetlands while I was away?
No.
Okay, are wetlands a poor option because of current guidelines that call for near zero selenium?
You know, I've seen different reports on wetlands. Some wetlands meet very low limits of selenium and others do not. And the point that we've tried to make is that when you've got to reach an ultra low selenium limit of say 10 parts per billion, 15 parts per billion on a consistent basis, because you don't have really good control in a wetland, that's really difficult to do. And it's not that we don't like wetlands, it's just that they don't have the same level of control as an active treatment or a semi-passive.
As mentioned, there are organoselenium species which are more bioaccumulative and toxic. These species are largely produced in biological systems where the selenium reduction is incomplete, either due to improper initial sizing of the system or poor performance of the operations. How are biological systems addressing this issue?
So that's a really good question, and I think it's fair to say that we are still, in my opinion, and this is maybe just my opinion, I think it's fair to say that we're still at the research stage in terms of determining all the reasons that you'll get organoselenium species formed. I know that the researchers at Arizona State University at ASU are looking at that. They're doing studies on why organoselenium species are formed and under what conditions. And then they're in the process of adding that to their CSANS model. I think it's fair to say that we don't know all of the reasons that organoselenium species are formed, at least not to my knowledge.
Okay. At sites like in the Elk Valley coalfields, selenium treatment could be complex in terms of scale and choosing the right technology. Any thoughts on this?
In what? So I'm not sure I really understand what the question is. You want to repeat that just one more time?
Yeah, I just lost it, but let me just see if I can find it again. At sites like the Elk Valley coalfields, selenium treatment can be complex in terms of scale and choosing the right technology. Do you have any thoughts on that?
Yeah, I mean, whenever you put in a treatment, whenever you put in a treatment system, you've got to look at your site. If you've got a limited space to put in a treatment process, sometimes that might force you to active treatment. If you've got the ability to create a saturated rock fill, and you understand that the long-term fate of selenium that's sequestered is still not 100% known, and you have some sort of backup plan in case it remobilizes, I think that, quite frankly, you'd go with that route because of the cost, right? It's half the cost. You've got to really fit your treatment process to your situation. And every site is different.
Right.
And every mine impacted water is different, right? Matrix different.
So given the uncertainties of various solutions and your comment about layers, I'm not sure what the layers was referring to, does this suggest investment is prudent in multiple technologies, supplying something like a factor of safety of less than one?
We answered that one, Brenda.
Oh,
Yeah.
you did. Good
Well,
job.
we were on that.
We got that one. That was our best answer, and you missed it.
I can watch the video, apparently.
That's right. All right, let's try to get one or two in here real quick, and then we'll wrap it up for everyone. And again, we'll follow up with you offline.
Do you consider more research is required for what happens to the selenium in wetlands, like wetlands at Comess Natural reduces selenium to undetectable?
Absolutely. And a lot of people think that wetlands are simple, okay? But actually there's a lot of things going on at wetlands. And whatever we can do on the research side to enhance our understanding of the dynamics within a wetland and all of the removal mechanisms that take place there will benefit the mining industry and other industries. So certainly that's research that I think needs to be done.
Great. Thank you. I think we will close it off
Wrap
there.
it up there? Okay.
Yes.
Yep. Thanks, everybody. Really appreciate it. We had, I think it's the most questions we've ever had. So great interaction. Thank you to the presenters. And again, a lot of you have asked about the PowerPoint. I'm going to ask you to follow up with Rob and Brenda directly. We don't typically send out the slides, but we do post recordings. A link is in the chat that will take you to the page with all of our past webinars, so you can view it on demand. But if you want the actual slides, you'll have to follow up.
Yeah, Ryan, I'm okay to send out a PDF of the slides if somebody wants that.
Okay, if you're good with it, then
there's nothing top secret in there. So
just reach out to one of us and we'll be able to help with that.
Yeah, I think that's the best approach. Okay, well, thanks again, everyone. I really appreciate it. We hope to see you on an upcoming webinar. Hope you have a good day.
Thank you, everybody.
Thank you.